Hello and welcome. I hope you are doing great. In this video, we are going to discuss about various performance metrics that are used to evaluate machine learning models. So I hope the screen is visible. Let's set up the agenda first. So these are the performance metrics. So we'll start with confusion metrics. That's the most common utility. Okay. Then we'll discuss precision, recall, F1 score, then ROC, receiver operating characteristics, and area under ROC, that is also called AUC, and then we'll talk about PRC or precision recall curve. And while discussing about confusion metrics, we'll also discuss about type 1 and type 2 errors. Okay, so let's understand all of them one by one. So all of these, so once the machine learning model is ready, so we need to evaluate, right, how is it performing on the test or unseen data. So when you have the regression kind of data, right, so that time we use the metrics are different. Okay, so for a regression kind of data, we use the mean squared error. That's the most common one, the mean squared error. Okay, and then we use mean absolute error also. Also we have R square metric for evaluating machine learning model, but this is for all for regression where we have numbers. Okay, when we have numbers changing. Okay, in that case we are using these metrics where we have numbers and we can do square and etc. and do multiple mathematical operations on that. But what to do when we have classification kind of problems? Binary classification or a multi-class classification. Binary means success, failure, yes, no, male, female. Okay, duplicate or real, something of that sort. If we have some classification problem, or multi-class, there are multiple classes also. So if you have classification problem, then whatever metrics we are going to discuss today, that is applicable for classification problems, where we have, it can be like binary, where we have only two classes, binaries for two classes, or we can have multi-class classification. Okay, so these we will discuss when we'll dive deeper into machine learning. And that time we have also discussed this in the past, but we will dive deeper into these metrics in another video. Today we'll discuss about classification problems and when a machine learning model is made to solve classification problems, how do we measure its performance? So let's start with the simplest one and most common, widely used, that is our confusion matrix. So let's understand this with the help of an example. What's the word confusion? So you see this confusion, right? So there must be some machine learning model must be confused around something. That's why this word confusion is there, and there must be some matrix or a tabular format. So that's where the name comes from. So let me give you an example that will make it very clear for you. For example, I'll just go with two classes. So binary classification for now. So that, and it can be extended to multiple classes also. So let's see, for example, we have an e-commerce company and which sells multiple variety of clothes. Okay, and it has images of all the clothes that are listed on its website. And now the e-commerce company wants to classify them as what are the different kinds of clothes available. Okay, and out of that, for example, let's see that we have shirt. Okay, say for example we want to classify two classes. Say for example we want to classify images of shirt and jackets. So there are a lot of images. Some of them could be shirts and some of them could be jackets. Sometimes when you have long sleeve shirts, it can be confused with a jacket also, and that will be very difficult for machine learning model to identify. And sometimes there are very thin jackets that can be confused with a long sleeve shirt. Okay, so let's understand what happens. So let's draw the matrix. So there are two classes. Okay, so on this side we'll put like what is the actual, we know what is actual label, we know the image. Okay, what it is, it has an actual label. And then this side we'll put all the predicted values. Okay, so let me draw one more line here probably. Okay, so this is it. So these are the images. we have actual image of a shirt, okay, and here we have that the model predicted this is the model's prediction. So model predicted this as a shirt, and here we have, say for example, actual jacket, and here this is the model predicted it as jacket. Okay, this is the actual side. So let me highlight. This is your actual, another color. This is your actual, and this is your predicted. Okay. So if the image is actually of a shirt and the model predicts it as a shirt, no problem. This is good. Okay. So the model has identified it well, no problem. Similarly, if it's actually jacket and the model actually a jacket and the model predicts it as jacket, no problem. So if it lies in this cell, this diagonal, okay, then there is no problem. Everything is working fine. So the model is working fine if it predicts it. Fine. So these are good places. Similarly, we can have multiple classes. They can be like t-shirts, okay, and more trousers, etc., etc. And then this can keep on extending, and we'll have this longer diagonal elements. And all this, okay, whatever is on the diagonal means whatever is the actual thing and what is the predicted. If they match, then that is good, no problem. But as I mentioned, a shirt can be confused with a jacket. Okay, so if a shirt, okay, and if my point of reference, if I'm looking with respect to a shirt, that is my actual thing that I'm looking for, that whether all the shirts are classified well or not. So if I'm looking that whether a shirt has been classified as a shirt or not, but if a shirt has been classified as a jacket, then this is called that it was a shirt, but the model predicted it was a jacket, but the model predicted it as a shirt here. So from point of view of shirt, this is a false positive. We call this as a false positive because the shirt say this is the positive label. So one, we can say this is positive and this is negative. So again, this is a negative. Just for reference, one is for getting the terms, understanding the terms. So that is my reference point. So with respect to shirt, okay, I predicted a jacket as a shirt. So this was not a shirt, but it was jacket. So falsely I predicted it as a shirt. So these are called false positives. I hope the term is clear. Okay, so this is a false positive because we have predicted it as positive, but actually it was a negative, which is not a shirt. Anything, it can be anything, but it was not a shirt. This is a false positive. And similarly, if you go in this cell, so this is called false negative. Okay, why this is false negative? These are all true. These are your true positive. If you say the terms, these are true positives. This is your true positive and this is your true negative. Okay, this is true positive because all is true. So the word you should care about is true. So this is true positive and true negative. With respect to one, I have marked as positive and negative. So these are true, no problem. Everything is working fine. But something has been falsely predicted as what it was not. The model confused a jacket as a shirt and predicted it as a shirt. So this is a false positive. And similarly, if you see false negative, it was actually a shirt, but the model predicted it as a jacket. So that is your false negative. That it was actually a shirt, but the model didn't identify it. It got confused and it predicted it as a jacket. Maybe its cloth is very thin, or some features it might have a collar or something, and it got confused because of the image, or the image may not be clear. So this classifies as a false negative. I hope the terms are clear with this example. So this is a false positive, this is a false negative. So the false positives, okay, these false positives, these are called your type 1 error, and these are called your type 2 error, false negatives. Your false positive is a type 1 error and false negative is a type 2 error. And this is called a confusion matrix because this is a matrix where we put all the data. It's a tabular format, and we see where the model is getting confused, and we measure the confusion here. All these diagonal elements, if all of them have all the values, and if all the non-diagonal elements are 0, then a model is performing very well. But in real world scenario, it doesn't happen. The model will be confused, as I said. if there is a jacket, okay, there is some jacket and it looks like a shirt, the model will get confused. Okay, similarly, if there is a shirt which looks like a jacket, thick cloth or something, then the model will get confused. Even humans can get confused. Okay, so that's the broad understanding. I hope the terms are clear. So we understood what is it. The false positive is a type 1 error and false negative is a type 2 error. Okay, if this is clear, then so let's take, I'll give you one more example for the false positive or type 1 error. Type 1 error, these are false positive and type 1 error. So for example, say that we predicted that a patient has diabetes, but it does not have diabetes. Okay, in a medical test, a patient, okay, we did a test and the test says that patient has diabetes. The test says, so this is like a model. The test says, let me top it off. So we did a medical test and the test says that patient has diabetes, but actually patient does not have diabetes. So this is your false positive or a type 1 error. Okay, the test was a false positive, falsely told that you have diabetes. Similarly, for a false negative or a type 2 error, this will be similarly we conduct a test and say that the person does not have diabetes. So we conducted a test and the test says that patient does not have diabetes, but actually the person has diabetes, and actually the truth is the patient has diabetes. So this is your false negative, right? This is your false negative. Actually the person had, but the test gave negative. Okay, I hope the terms are clear now with more examples. So if this is clear, let's define some more terms based on, everything will be based on this. Now if this true positive, true negative, false positive, false negative is clear, now everything will be based on these terms. So the next term is precision. Precision literally means how correct or how exact we are with our prediction or whatever claim that we are making. Similarly here, so the precision is the how of all the instances the model predicted as positive, how many were actually positive. So if we take that shirt case, okay, actual shirt, if we consider that as a positive, so of all the shirts that the model predicted that it is a shirt, how many were actually shirt? This ratio, this is the precision. Okay, this part of all the predictions made by the model that these are shirts, which were actually shirt. These were actually shirts, true positives. These are false positives, these are not shirts. So this is your false positive rate. So what is precision? This is your, what will be a ratio? This will be your true positive by true positive plus false positive. I hope this is clear. It measures the quality of your predictions. Out of all the predictions you made for positive class, how many were actually positive? Of all the predictions you made about the shirt, how many were actually shirt? Okay, these were falsely made, declared as shirts. Similarly, there is another metric called recall. Okay, and the recall is, what do we mean by recall? So of all the actual shirts, so actually these were all shirts. Of all the actual shirts, how many were you able to identify correctly as shirts? Of all the positive instances, okay, how many was the model actually able to identify as positive label? Or of all the shirts images that I had, how many, okay, these are the actual shirts. Of all the shirts, how many was the model able to actually identify as shirt? So this is in this direction. Okay, so this will be your, of all the shirts, how many was the model able to correctly identify as shirt? So this will be true positive plus false negative. Some shirts were not identified as shirts, so I'll include these now. So this recall says that how much, whatever it has seen, how much it was clearly able to recall. So it will be true positive plus false negative. So it will give you a just quick hack. If you put actual here and predicted here, and the positive class first and the negative class second, so everything on this line, okay, this by this will give you your precision, and this by on this line, this will give you a recall. So here you will get precision, here you will get recall. If predicted is here and actual is here. Just a shortcut to remember, but you can just plot it, and if the concepts are clear, you will figure it out. I hope recall is clear. This is your recall. So if precision and recall is clear, then we will move to the next topic, that is your F1 score. F1 score is nothing but it's harmonic mean. So you have arithmetic mean, right? So similarly, we have harmonic mean of precision and recall. And there's a reason, okay, there's a reason why we take harmonic mean. I'll demonstrate that with an example. So this is a harmonic mean. So what will be the formula? So F1 score will be, so this is one of another scores to measure the metrics. It is just using precision and recall. So there's nothing new, and it's just a harmonic mean of the precision and recall. The formula will be 2 into precision into recall by precision plus recall. Okay, precision plus recall. So harmonic mean analyzes extreme values. Okay, whenever we have one value as extreme in this, in this, any of them is very extreme. Okay, and this will range from 0 to 1, right? So because the max can be 100%, so this will be 1, and the min can be 0. There can be, it doesn't identify anything as positive. So minimum will be 0, max will be 100. So these values will range between 0 to 1. Similarly here also, because that's the harmonic mean of that. So for example, if I have two values, if I'm getting precision and recall, let me show you an example. For example, I have precision score, I have recall, I have got this from the model's values what it has got, and I have got F1 score. And say for example, I have arithmetic mean or average. I'll write average, that is a common term that we know already. Okay, so say for example, if my precision is 0.5, my recall is 0.5, so what will be my F1 score? 2 into 0.5 into 0.5 by 0.5 plus 0.5. This denominator will be 1 and this will be 0.5, because 2 into 0.5 is 1 and remaining will be 0.5. So this will be, sorry, this will be equal to 0.5. Similarly, I will just write the other values directly. So this is how you calculate. So the average will of 0.5 and 0.5 will be 0.5. So next we'll say for example, if my precision is 0.7 and recall is 0.3, then similarly if you calculate, you will get a precision of 0.42. But what will be the average here? Arithmetic mean. Now you see the precision has improved, but the recall has gone down. But still my average will be 0.5 only. But you see now it has become less because the recall has gone down. So it should show that it is less. This is not, means this is worse than the previous score. Similarly, if the values become more extreme on one side, say for example, if I have 0.9 as precision and 0.1 as recall, so what will be my average still? It will be still in the middle. But the recall score, if you see, this will go down to 0.18. So this is the beauty of F1 score, that it penalizes extreme values, and because of that, that impact will be visible in the F1 score if any of the values is very low, and because of that the F1 score will go down, but the arithmetic mean won't show that. I hope this is clear. So this is your F1 score, simple. Now I'll give you a note when precision will be important. So there are two metrics. So out of this F1, you have to balance in the F1 score, right? Which one should I go for? If one goes up, other will go down, right? So there will be always some trade-off between them. And finally, so when should we focus for precision? So when should we have precision focus? So when should we have precision focus? So whenever the cost of making false positives is very high. So whenever we have the cost of making false positives is very high, because that's what it captures, because the false positive is very high, because this is same, true positive is same, but the cost of making false positive is very high. Okay, then this is the error we are making, right? So when the cost of making false positive is very high, in that case precision, okay, then precision should be focused. False positives are very important. For example, say for example, I have an algorithm to, or some way, a mechanism to identify a potential terrorist. Okay, for example, when we want to identify a potential terrorist, so if we say falsely, okay, if there's a false positive, means there is some innocent person whom we falsely identify as a terrorist, that will be very detrimental to that person's life and quality of life. Some person can be put into jail for no reason. Okay, so when we falsely identify a person as a terrorist, okay, so these false positives are very dangerous, and that's when this precision focus becomes important. Similarly, the other way around, when should we focus on recall? Because this F1 score is a harmonic mean. So when the false negative, the cost of making false negative is very high, the impact of having false negative is very high. So what is such a case? Say for example, if we are having a test, medical test for a very serious medical condition, that time, okay, if a person has that disease and we miss to identify that disease, falsely we say that no, this person doesn't have that disease, in that case false negative can be very costly and it can cost some person a life. So that time we should be very focused on recall. So I'll give you the example. For example, medical diagnosis of a serious disease, medical test or a diagnosis of a serious disease. We should not falsely miss to diagnose this, any test. So that time the cost of false negative, and we should focus on recall that time. Okay, so I hope this is clear. So let's quickly put some numbers and understand this. So let's put a problem and understand this. So I'll just put, you will have the numbers, and now if you've got the fundamentals now, then it should be very easy. Say for example, I have access card in the company. Okay, so I have access card for authorizing someone to let in, or unauthorized if somebody doesn't have an ID card, or any website also, right? Access we have. So somebody who has a valid identity will be authorized to get in to the office, and somebody with no ID will be not allowed into the office or in the system or on the online if you try to log in. So this is what my access system is doing. So so we have a data for n is equal to 1000 access attempts, maybe your office or some website. Okay, so now let's draw the confusion matrix for this. So this side I'll put my actual data, here I'll put my predicted data, and then let's draw the matrix. Something like this. Okay, whatever, the last line may not be, that is okay. This is there. So this is actual is there. Okay, so someone who is actual, I'll leave this, I'll write here, actual authorized to enter, and then you predict, or the system predicts that this person is authorized. Okay, and then there is some actual unauthorized person. This person should not be let in the system, and now the system will have some bugs. If it's a software system, that may have some bugs. Okay, and then this predicted unauthorized access. Okay, so this is the data we have. So the data what we have is, here we have 90, 10, 1, and this is 899. Okay, so whatever comes in my diagonal elements, these are good because this was actual, predicted actual. This was authorized, predicted, authorized. This was unauthorized, predicted, unauthorized. All good, no problem. But the confusion is here. Okay, that's why it's called confusion matrix. So this is your true positive. This is your true negative. No problem with this. The problem is with the your false positive and the false negative. So somebody was actually authorized and you predicted authorized, no problem. Somebody was actually unauthorized, you predicted unauthorized, no problem. The access system is working fine. But if somebody was actually unauthorized and your system predicted it to be authorized, maybe that person is a hacker or with some fake ID, somehow that person got into the system. So, but only one person was allowed. So still the system is performing well. Okay. So this is good. And now, so you let one hacker in. So we'll calculate, because the system won't be 100% proof, right? So we'll calculate all the values, precision, recall, F1 score for this. And similarly, somebody was actually authorized, but the system predicted it as unauthorized. Maybe the access card is broken or the magnetic strip is not functioning well, or there is some problem, some fault happened. So actually, these 10 people faced some hassle from getting authorized, and the system flagged them as unauthorized and they were not let into the system. So this is the whole problem. And now let's quickly do all the calculations. We have all the numbers. So what will be my precision? My precision is true positive on this line. True positive by true positive plus false positive. This is equal to 90 by 90 plus 1. This will be very high. This is equal to 0.989, approximately 98.9% precision. Very good. The system is very exact. What will be my recall? Recall is on this line. So this is your true positive by true positive plus false negative. So this is your 90 by 90 plus 10. So this is your 0.9 or approximately 90%. So even your recall is fine. Okay, only 10%. So 90 and 99, almost 99%. So what is my F1 score? So this is 2 into precision into recall by, I'll shortly write P plus R. Okay. So this is 2 into 0.989 into 0.9 by 0.989 plus 0.9. So this will come out to be approximately 0.942. So this is a very good F1 score, because yes, already my precision and recall are good. So this is your F1 score. So this is how you calculate. So I hope with numbers now it should make more sense and it should be very clear. So if F1 score is also clear, so these are the parameters that we deal with a lot. Then let's move to the next topic, that is receiver operating characteristic. So receiver operating characteristic. So these terms, whatever this term, this has been borrowed from signal processing or communication technology. Okay, so this term is coming from there, and I'll explain you what it means. So these kind of curves. Okay, so machine learning, as I mentioned earlier, is borrowing concept from lot of other fields. Okay, so it's not one field and characteristics from lot of fields of maths, and it keeps on borrowing concepts from everywhere, whatever is good. Generally, software engineering in general, it borrows concepts, all the design patterns, etc. It keeps on borrowing concept from all other fields and it applies it. Okay, and that's good. That's how it should be. So this is ROC. This is called ROC, borrowed from communications or signal processing technology. Okay, and there we just plot graphs. Okay, so we plot a graph to understand how the model is performing. This is for binary classification. Okay, binary classification. Confusion matrix can be for any number of classes. Okay, the number of classes can go on increasing, but this is generally for binary classification. Okay, so these are graphs. So binary. So we'll put one parameter on one axis, other parameter on other axis, and we'll measure. So what is there? So let me move this to the other page itself, and then this will make sense. Let me stretch it a bit so that it becomes clear. Okay. So say this is your graph. So on the y-axis, so what are we plotting here? So it is a curve, it's a graph that we plot. Okay, it's a plot or a graph to understand the models, a binary classifier performance. Okay, we have written models performance on binary classification task. Performance. Okay, so this is y, this is x axis, but what is there actually? So y axis has true positive rate. So I'll write it here. So y axis has true positive rate. What is true positive rate from here? So true positive rate, we know that is your, out of all the truths, how many? Okay, so this is your true positive rate. Out of all the truths, actual truth, how many was the system able to actually identify as true? So this is your true positive rate. So actual what was true, of that how many the system was able to identify true. So this is your true positive rate. So y-axis is TPR, that is TP by TP plus false negative, that is true positive plus false negative. This is on the y-axis. And on the x-axis we have, we have false positive rate. Okay, this is your FPR. And how is it defined? False positive rate, this is your false positive by false positive plus true negative. So this is, so y-axis is coming from here and the x-axis value is coming from here. So this by sum of this and this. On y-axis, true positive by sum of these two. False positive on the numerator and the sum of these two. So if you plot these graphs clearly, so you will have. So we have precision here, recall here, okay, and the true positive rate here and the false positive rate here on this. Okay, so we have these values and we plot this on this x and y axis. So here we have true positive rate and this side we have false positive rate on the x axis. So what do we do here basically? So whenever we have, so if you know a bit of machine learning model, so output for binary classification model is a probability score. Okay, and then we have a threshold. So generally the output for model is a probability. So it will be in the range of 0 is less than equal to, the probability is less than equal to 1, in the range of 0 to 1. So the model outputs are some probability of that being. So for example, if I'm doing a cat dog classifier or even never shirt jacket classifier, so it looks at the image that it has and will give you a probability of that from 0 to 1 I am having this confidence that this will be a shirt. Similarly for jacket, okay, it will give a prediction score that this is the, or say for example it is saying that for some prediction it's saying that with 0.8 probability this is a shirt, and for some other image it is saying that that I only have 0.3 probability that this might be a jacket. So we have these values for certain images, and after that we fix a threshold. Generally by default it is 0.5. so this is your threshold. So if the probability value, this p value, okay, if this is greater than whatever p the model is predicting, if it is greater than equal to your threshold, which is in our case 0.5, then this will be classified as one class. Say for example short, this is 1, this is 0, this is binary classification. Okay, so I classify it as 1, and if it is less than 0.5, then I classify it as a 0. So whatever is my threshold. So for this jacket, for something to be classified as jacket, I will just focus on whether it's shirt or not, with what confidence I'm predicting it. And for the jacket, it will just say that it is 0.3 probability that it is a shirt. So this will automatically be classified as jacket. If it is not shirt, then this is a jacket only. If it is not 1, then this is 0. Only 2 options I have. So that's why it is a binary classification. Okay, so this will be classified as 0 because it is less than 0.5. So this is how we do. These thresholds are 0.5. Generally it varies depending upon our requirement. Sometimes we have 0.6 or 0.7, whatever, it depends on the use case. But mostly for our practical purposes, we consider this as 0.5. Okay, I hope that is clear. So this threshold depending upon how the model is predicting. So now when we are doing the actual classification, say for example, I have one patient, okay, and let me see the example. Say for example, I have a patient and then I am classifying it as a true false, okay. So this that will be easy. So whether has diabetes or not. So has diabetes is 1, not is 0. No diabetes, okay, no diabetes. So I have a test to predict this. So if it has a diabetes with what or a no diabetes, if it is greater than the threshold of that test, then this will be diabetes. If no, there will be some like kind of sugar in the blood, right? So that test is being done, and then if that is less than that threshold, then it will come to be 0. For us, let that be 0.5. So we have a data, say we have a patient ID, and then we have the true label, that is the final label that we have, and then we have the predicted probability. So what is the true label? Finally, we don't need this these probability values, right? We finally need it as 1 or 0. We want to know whether whatever the test value comes, it will come in the range of some range, right? Some value. But after that, I only want to know whether it has diabetes or not diabetes. That's what is my final binary conclusion. This is what my test is for. Say for example, patient ID 1, okay, the true label is 1, and the predicted probability for diabetes is 0.95. This is generally called as y hat, okay, and this is your predicted label is yi, and x is the input. So I have 1, 2, 3, say 5 patients are there. So true label is 1, 0, 0, 1, 1, 0. So 1 means has diabetes, 0 is no diabetes, and the predicted probability with which this came, okay, that is 0.85. This is actual, okay, this is actual. This is the actual, this we know, but this is another test, okay, which is the model is giving me. This is actually whether the patient has the diabetes or not, we know, but we are just verifying whether the test is model. How is the model performing? Because always the model will be trained with some known data. So this is a known data. This is the ground truth. Okay, I know this for sure. And then I'm checking what is the model predicting and how good is the model predicting. That's what I want to see. I want to see the model's performance. This is your model's performance. Okay, whatever algorithm we have given. This is the ground truth. Okay. So this is your 0.85 probability. Then we have, say for example, this is for 0.70 probability. Then we have 0.45 probability, and then we have 0.20 probability. Something like this, okay. So we have these values. Okay, this is true label or actually whether the patient has or not. So now what do? We have this data for receiving receiver operating characteristics. So how do we plot? So we have to calculate true positive rate and false positive rate. Here if we have one data, so we'll get only one data point, but I said it is like a curve. We'll get a curve like this. So we should have multiple data points, right? Generally it's a curve. So this is like this one line. You will get a curve like this, some curve. Okay, but if I get a true positive rate or false positive, because I can count all the ones, I can count all the zeros, that will come to only 1 point. How do I get many points to plot the curve here? So what do we do here? So what's the algorithm? So what do we do? So algorithm here is sort this. We have already sorted this, okay. Sort the data in descending order of probability score. So first thing is sort the data in descending order from largest to smallest, descending order with respect to your model's probability score, whatever probability score it is giving. So sort the data. We have already sorted this, okay. And then what do? We set each probability score as threshold. So earlier I told you, right, it can be 0.5, but what we do now, we set each probability score as the threshold, and then we try to classify. If 0.95 was the threshold, say for example, then only, okay, anything above this is diabetes, say for example. So only this will be classified as 1, rest all will be 0, 0, 0, 0. If this is my threshold, 0.95. Now if I set my threshold to 0.85, this one, this will be 1, this will all be 0, 0, 0, 0. Similarly, if I set my threshold to 0.7, this will be 1, 1, 1, this will be 0, 0, and so on. I hope you get the idea. So I'll set each value as a threshold, and then based on that I'll give my final label, predicted label. and then I'll plot. Then I'll calculate my true positive rate, false positive rate. Earlier, this is the actual thing, but now you see the true positive rate and false positive rate will change. Here, if I put 0.95 as my threshold, I'll have only 1, 1 and all will be zeros. My true positive rate will be less. If I set 0.545 as my threshold, I'll have 1, 1, 1 here till here, and this will be 0. So I'll have 4 positive, okay, and only 1 negative. So my true positive rate will increase. So this is how we are getting. So for each threshold, we calculate, we set each threshold as each value, each probability score as a threshold. In the second step, set each probability score as threshold, and then a threshold for classification as for one, or whether it is 1 or 0 or positive or negative class, and calculate my PPR and FPR, because that's what will go on my x and y axis, and each points will get, sorry. So we'll calculate PPR and FPR for every threshold. Okay, so for example, I have, so whatever I have said, I'll just write it on the next page. Say for example 1, my threshold is equal to 0.95. okay, so I'll calculate PPR1, FPR1. okay, then my threshold will be, for this is for step 2, okay, step 2 only, 0.85. then I'll calculate PPR2, FPR2. so these are different points. okay, and then slow like this, I'll calculate PPR n, FPR n for n points, and then finally now I have n pair of points, one from y-axis, one from x-axis, x-axis, y-axis, other way around. okay, and then I can plot this on my coordinate system or on the graph. okay, and finally we can plot this on a graph. And let me copy this. And then you will get a curve like this. So you will get a curve like, let me draw one. Something like this for where 0 is 1. okay, so say this is 1, this is 1, so this is y is equal to x, everything is same. This is your, so this is y equal to x, this is 1 and this is 1. so this is your, any random model can predict this. If I randomly classify all of the labels as 1 or 0, then half of them will be 1, half of them will be 0. So after that, when we calculate this will be my, I'll get just a straight line where half of it is means all the true positive rates and false positive rate will always be same, because randomly it will classify half of them as positive class and half of them as negative class if I have just a random model, because it will do 50-50. And then anything better than this random model, say for example if I have this curve, the true positive rate is there. So what will be the best model? First let's understand that. okay, so what should be ideal true positive rate? So my true positive rate ideally should be 1 and my false positive rate should be 0, right? That's how it should be. So ideally my curve should be here. So I should have some, let me draw like this. So I should have, my graph should be like this, that my model is predicted perfect. It has not given me any this is a perfect model. okay, it is not giving me a probability of 0.95, 0.85 like that. If it is a correct thing, it will give me a probability of 1. okay, if it is it has predicted, it is a perfect model, it knows, it will not give me a probability of 0.95. it will always give me 1 for the positive class and 0 for the negative class. So when I set threshold as 1, everything, all the true positives will come together, and otherwise if I set threshold as 0, everything will come as false positive, right? So my true positive rate will be 1 always, and my false positive rate will be 0 always, because everything will be correctly classified. So I'll get this point because this is your 0 here. Let me come back. Okay, this is your 0 here. So this is your x is 0, FPR is 0, and true positive rate is 1. So this is your perfect model, but that is not happening. My model will not be giving like perfect 1 and perfect 0 probability output, because there will be some confusion always, and it will be there be some gray area because the images may not be clear, and definitely even we get confused. So this is the ideal case we should have. And anything, this is a random model. Randomly, if I classify 1 0 1 0 1 0, half of them as 1, half of them as 0, then you'll get this line. Okay, anything better than this, so this is your worst model. Anything below this, we'll talk about this later, it will not go there. So this is your worst, this is your best. So anything be in between this will be your good model. So let me draw one more, maybe something like this. So for each of the points that TPR1, FPR1 we are calculating, right? So we'll get these points here. Say for example on this line, so you will have these points like this, and then it's all the points. So this is like TPR1, other way around, right? FPR1, the x-axis will come first, comma TPR1. Then similarly, like this will be TPR, other way, FPR, some kth point, and then TPR, kth point. This will be here, and then this you will come here. So we'll have some FPR, nth point, and TPR, nth point. So for all the thresholds, for each threshold, whatever you have calculated, we'll keep plotting it, and then we'll get a curve like this. Okay. And I said that this is your worst model. Anything cannot be worse than this. If I randomly put 1 zeros, so I'll get this half of them as positive and negative labels randomly. If I put my true positive rate and false positive rate will be equal, this is the worst that we'll get. You can do the maths and check and say why can't we get something like this? Because if you see, if I'm getting something like this, for then that is coming like true positive rate and false positive rate. So if I flip the labels, if I make positive as negative and negative as positive, then will this not curve anything that is coming? This will just shift that the other way around. The true positive will become false positive, and this will just shift the other way around. So means whenever you're getting something in this zone, means you can just flip the labels, that whatever is your positive label, make it negative and vice versa, and then this curve will automatically come on this side. I hope the receiver operating characteristic curve is clear. And this area, ideally, okay, this area under the curve, okay, this area, this is your ROC, this curve, okay, this is called receiver operating characteristics. And the area under this, so area under ROC is also called area under curve, AUC, or AU-ROC. So whatever is the area under this curve, okay, this area, if this is the case, then the complete area will be there. So this area is called as AUC, or area under ROC curve. In short, AUC, area under curve, area under receiver operating characteristic. I hope AU-ROC is clear. Okay. And the random models, because it will randomly classify everything as half of them labels will be classified as 1 and half of them will be classified as 0. That's why you will always have the true positive rate and false positive rate will be equal, and they will be on a y equal to x axis. So this will be like half of. Okay. So but this has limitations, and we'll understand it with an example. So ROC is not the right. Okay, just note it that ROC doesn't work well with imbalanced data. ROC does not work well, or it does not give right output with imbalanced data. What is imbalanced data? Imbalanced data means I have more data from one class than the other class. That is imbalanced. If I have equal number of samples from positive and negative class, okay, then it's not a problem. But if I have lot of samples from the negative class and very few samples from the positive class, then it is a problem. That is called imbalanced data. And because of the formula for the false positive rate, which is your, what is the true positive rate and false positive rate? So just remember this. Okay, what are we plotting? Because of the formula of the false positive rate, this is the problem. I'll give you an example, it will become very clear. So whenever we have imbalanced data, ROC doesn't function well. And let's understand what is an imbalanced data with an example. Say for example, you have a fraud detection system. Okay, so whenever you have a fraud detection system, for example in the bank, what are fraudulent transactions? Okay, you have fraudulent transactions. So the number of fraudulent transactions will be very, very low. Compare it with the number of transactions happening in the system. The number of fraudulent transactions will be very low. Okay, that's what is the imbalanced data. For example, if you have millions of transactions, out of that maybe 1% is fraudulent and 99% is a normal data. But 1% at the bank scale is also a big loss if the amount involved is high. But the number of transactions, if we compare, the number of transactions will be very few. So that's the imbalance we are talking about. And we will see how with the numbers that why this, because of this false positive rate, the way it is calculated, ROC doesn't work well on imbalanced data. Okay, so let's do a fraud detection system with n is equal to 10,000. I have 10,000 transactions data. Okay, and we have fraud entries as 100 and not fraud is 9900, right? Yeah, 9900 plus 100 is it's 10,000, right? So it's 1,000, 10,000, right? So this is your fraud. So let's again plot it the way we do it. So this side it will be your actual, this side will be your predicted. That what is my model predicting? The fraud detection system. Okay, so let's write here. So this is your actual fraud, and this is predicted fraud, and this is predicted not fraud, and this is your actual not fraud. And let's draw the lines. So for example, this is your actual fraud, actual not fraud. So say these are the lines, and we have that what the values we got, that we have total 100 frauds. So actual fraud are total 100. So this is 80 and this is 20 and this total is 100, and the not fraud is 220 not fraud here, and here the remaining 9680. So as I mentioned on the diagonal, whatever, if it is for actual fraud, predicted fraud, no problem. Actual not fraud, predicted not fraud, no problem. This is very good. Okay, so these diagonal entries are fine, that whatever is actual, that is detected by the model also. So these are your true positive and this is your true negative, no problem, these are good. This is your, actually it was not fraud, but you predicted it as fraud. So this is your, if fraud is a positive label, then this is your false positive. So this is your false positive, and similarly this will be a false negative. Actually this was a fraud, but this, your system was not able to catch it. It said that no, it is not a fraud. Okay, so what is your true positive rate here? So what does it plot? This, let's calculate this. So once we understand how to put this true positive, false positive, so just putting in the formula is simple maths. Okay, so what is the TPR? That is true positive by true positive plus false negative. So this is your 80 by 80 plus 20. So this is fine. This is your 0.8. No problem. What will be a false positive rate? So this is your false positive plus true negative. So this is your 220 by 220 plus 9680. So this will come approximately, this will be equal to 220 by 9900, and this will be approximately equal to 0.022. 0.022. And here if you see that if something is very good, if the model is functioning, all the points, okay, everything will be done perfectly fine, and all my points will be for a perfect model 0, 1, 0, 1, everything will come here only. And if for some worst model, all the points will come here like that. Okay, so the further away from 0 and closer means if the true positive rate is high and the false positive rate is low, then that is a good point and the model is functioning well. Right, that's the measure. That's the measure here. So let's see. So this is a 0.000. So what will be my ROC point here? What will be the ROC point? If I put it on the curve, ROC point will be equal to my false positive rate, that is on the x-axis, comma 0.8. So this will be somewhere on the top left corner, as I mentioned. That means top left corner means it is somewhere on the top here. 0.8 is here and 0.022 somewhere here. Means my model is performing really well. If I plot, if it continues here, the model will give me that okay, it is performing very well on the model, on the given data. Okay, and this will tell that okay, the model is performing very well. But let's see, here also you can see that the actual predicted fraud. Just check that. So what will be the precision of this model? That is, what is the precision? If you remember, that is true positive by true positive plus false positive. As I mentioned, it is here on this line. So true positive by true positive plus false positive. Okay. So what will that be? What is the precision of this model? That is 80 by 80 plus 220. That is equal to 80 by 300. So that will approximately be around 0.266267. Okay, so this model has such a poor precision. Out of 300 frauds, okay, it is only able to predict 80 as fraud. 220 it is not able to catch as fraud. It is telling that no, it is not a fraud. So that is so much of loss. So the precision of this model is so bad. And that is because of the data imbalance. If you see from this perspective, because this number is very large, the false positive rate will always be very small, and you will see that okay, the points will always be on the left side. This will be very close and it will go very high on this side. Okay, it will never come on this side and it won't go down. So because of this imbalance, okay, which is pulling the values of false positive rate to a very, very small value, and this imbalance is causing all the problems. And that's why ROC is not so good for imbalanced data. I hope that is clear. And the better thing, as we saw, that this TPR is nothing but your recall also. This is your recall. True positive rate is recall, right? So what were we doing? This is your recall also. True positive or true positive plus false negative. So if we replace this false positive rate by precision that we saw here, that will give me the correct information that okay, this is very poor, the precision is very poor, right? And that's what gives rise to the solution for this, that is your precision recall curve. Let me write it in a different color. So this is a solution for this problem. For imbalanced data, we go for precision recall. We know both the metrics, okay, or PRC. So this is your precision and recall curve, and this is used when the data is imbalanced, and you will get a curve like this. So the process to plot the curve is same. You have that all the points similar to ROC. We get all the values, patient ID same thing, and we have all the predicted probabilities, and for each threshold we calculate the instead of one was true positive rate and false positive rate. Here in precision recall curve, here we will have true positive rate, which is recall, and we have false positive rate, which is your there instead of false positive rate we'll replace this with precision. So this will become a precision and recall curve. Same process, everything will be same the way we did ROC. So follow the same process as ROC to plot the curve. Plot the curve similar to ROC, follow the same steps, and then what is the precision and recall, and finally you will get some curve like this. I'll just write and you can just check online. So the curve would be something like this generally, okay, something like this, okay. And this is from, yeah, this is the best would be 1 1 here, okay. And this would be so the best curve would be like this would be 1 comma 1, right? So the best curve will be like that, okay. This will be our best curve. This will be the 0 point, and the area under the curve, sorry, let me use another color. So this area under the curve, similar to that, will give me your area under, this is called area under PRC or area under precision recall curve, this area here. And here what all we on the recall, okay, here we have recall, here we have recall on the x-axis and precision on the y-axis. So this same precision was also called false positive rate in the ROC. So this remains same, and the recall. So this is the recall was here. Recall was the false positive rate. Sorry. So that has been swapped. So that's why the curve structure also. So this is your false positive rate, true positive rate. Okay. So your true positive rate is your TP plus Fn. Yeah, this one. So this is also a recall. So if you go this true positive plus false negative. So this is your recall on the x-axis and precision on the y-axis. And if you plot this, you will follow the similar steps as ROC, and you will get the precision recall curve. I hope this is clear. Okay. So if this is clear, let's do a quick revision. We did a lot of things. So what all things we covered? So we understood what is the confusion matrix using this shirt and jacket example. So anything which is around this, that is fine. That what was the shirt was predicted as shirt, and what is not shirt, or a jacket which is not shirt is predicted as not shirt. So this is called true positive. If I classify this as positive and negative, so this is called true positive, and this is true negative. And what is actually positive and classified by the predicted by the model as negative, that's called false negative. And what is predicted by the model as false positive, but it was actually a negative class, this is called false positive. The false positives are also called type 1 error, and the false negatives are also called type 2 error. These are just names. Okay, you can plot this for anything, and these are called positive, positive, negative. You just plot this actual on this side and predicted on this side. So we have now false positive rate. Okay, so we calculated a lot of metrics around this. So first we understood what is precision. Precision is how exact the model is. Means if something is positive, okay, something is positive, how many of that was my model able to identify as positive? So that is my precision. And the recall was out of all the actual positives, how many was my model able to identify that, okay, these are the positives, and rest, okay, it falsely identified as negative. So around this is a precision, that out of actual positive, whatever it is predicted. So this is in terms of prediction. So your precision is in terms of prediction. Okay, so whatever it is predicted, out of that actually how many were positive. And the recall is the other way around. Out of all actual, how many was the model able to tell that, yeah, this is the positive label. Okay, that's the precision recall. The formulas are here if you follow this. And then we understood F1 score, that is nothing but a harmonic mean of precision recall. And we understood why it is a good metric instead of arithmetic mean. Then we saw an example to understand. So that is then we understood receiver operating characteristic. We understood how are we plotting it using threshold. For various thresholds, we plot the true positive rate and false positive rate. So the true positive rate is coming from here. So this is your true positive rate, and the false positive rate is coming from here. So total by true positive, total by false. False positive by total, false. True positive by total is true positive rate, and false positive by total here is the false positive rate. So we put plot this on the x-axis, this on the y-axis, and the final curve that we get for various thresholds, that is called your ROC. And any random model which predicts randomly as 1 1 0 0 means half of them as 1 and half of them as 0 classes, that then that is your worst model. Anything cannot be worse than this. If something is coming here that is worse than this, then you just flip the labels and the curve will turn other way around. and that will not be so worse. And the best model is, a perfect model is having all the points here only 0 at 0 1. Okay, because the probability scores are not some fractions, but for one class it will give 1 and for 0 it will give 0 only. Okay, and then we saw how ROC doesn't work so well with imbalanced data, and the solution for that was precision recall curve. And the precision recall, we plot the recall on the x-axis and precision on the y-axis, and the area under this curve, this is not so smooth generally, this you will get some jagged like this generally in practice, and that is good enough. This is, you won't get a smooth curve mostly. And the area under this precision recall curve is called AU-PRC, and the area under the ROC is called AUC or AU-ROC. That's all. Okay, if this is clear. And the most important thing, these all, okay, whatever we have shown, this is for classification problems, a binary or a multi-class. So the AAC PRC is for binary classification, sorry, and the confusion matrix is for multi-class. Even for multi-class it will give. Generally whenever we have some classification output, we do a confusion matrix and see how is the model behaving. That's the first thing that we look at. So these are all for classification problems. And for generally for regression, we have mean squared error, mean absolute error, and R-square metric. That we'll see when we do machine learning videos. Okay, I hope this is clear. Okay, and thanks for watching this video. Have a good day and bye for now.